Good afternoon and welcome to the National Centre for Nuclear Robotics live stream demo event. We are looking to live stream today from two remote locations. We have Professor Mark Hanheider in Lincoln and Professor Tom Scott at the University of Bristol. So I will be just handing over now, or introducing Professor Mark Hanheider. So Professor Mark Hanheider, welcome.
Hi. Pleasure to be here. Really good to be here.
So how's everything over at your end? The robots looking like they're about to play ball?
I think the robot over there is hopefully ready to operate in it, together with this one on my other side. And we're going to do a bit of a demo of mobile manipulation with some teleoperation in there and some navigation aspects. So bringing together quite a few aspects from our NCNR involvement here.
Wonderful, fantastic. Thank you, Mark. So we should be having Tom Scott joining us live from a field in Bristol with his drone. Unfortunately, he's just having a few technical issues there at the moment, so I'm just going to show you what he was going to show, but he will be joining us at past. So if you are able to rejoin us at 4:30, Tom Scott will be here live, and he will be showing this drone here. There's Professor Tom Scott.
And
Okay, so if you didn't quite get that, so what they've done is they've hidden a radioactive source, a radioactive piece of material in this long, tall grass. They're going to take this drone off, which has a radiation detector, and they will be searching for that radiation hotspot so that they can then, rather loud, and the idea is we have two separate demos today, but the Lincoln demo would link to this if they were outdoors in the same field. Oops. Okay, so that gives you a little bit of a taste of what Professor Tom Scott is doing there in Bristol. As I say, he'll be doing that again live at 4:30. As you can see where I'm here, I have lots of screens, and what we're basically simulating here is that we have a base operator who's talking to different vehicle experts who are using their different technologies to actually overview a scene, find radiation sources, and interact with that radiation components. So I'm just going to add Professor Mark Hanheider back in here now. Hi, Mark.
Hello. Yeah,
Right.
I don't think if the audience heard much of that what's going on there. Seems to be a bit technical glitches, but happy we're back. I hope you can all hear me by now.
Could you not hear the audio on that stream?
No, we couldn't. I tried to do a bit of a voice over there. But
okay. I saw you wave your arms around. Well, thanks for trying. Okay,
that's all right.
So, Mark, do you want to overview what you're going to demo today?
Yeah. Let's talk a little bit about what we're doing in NCNR. And I have a few slides that I can talk you through briefly. I hope you can see them. Otherwise, Peter, if you make sure that they are actually live and in color, that would be appreciated. Our focus is that we are really here looking at closing the loops. We're closing the loops between navigation and manipulation. So we're talking about mobile manipulation to be able to go about these sort of environments that we've just seen. And we will also see that we're closing the loops between reality and simulation, because in particular, when you deal with radioactive environments, we don't really want to have lots of radioactive sources around in our environment. So we've actually worked quite a bit to facilitate also the development of digital twins. And we're keeping also the closing the loop between humans and robots, because we, especially in a domain like nuclear, you really want to have the experts in the loop. So which is why there's a lot of effort also in teleoperation. So we're going to talk a bit more about that and see some simple examples of that. I have heard one cannot see my slides. So Peter, can you make sure that my slides are visible? Excellent. There we are. So that was the loops I've been talking about. I'm moving forward a little bit, and you will find that what we are doing also at Lincoln is not only nuclear robotics. We have also a lot of effort and lots of works going on in the agricultural domain that you may already have heard about, while we're doing a lot of work in strawberry picking, phenotyping in fields, etc. And we're using a same platform as the mobile base here, and a lot of the technology is actually shared, because while nuclear is an extreme environment, and so is agriculture. Well, the whole story here is, if you look at the little video that you've seen before, where we had a drone doing a reconnaissance mission of an outdoor field, we can do the very same also with a mobile base that goes about in a field as we see it down here. This is more from our agricultural campus, and I'm just going to say, like, there's an interesting link between these two domains for us that we're really trying to exploit. And this is a link between a simulation, a gazebo simulation that you see here on the left, and the real world environment. No, sorry, no, you see the simulation on the right, and a real world environment that you see in this little video here. And the concept is really that we can just populate the virtual world, which is linked to the real world, with some artificial information, which is a really powerful tool overall to do a lot of these experiments. What we're showing here is basically a Gaussian process, as we call this, which does mapping and actually is able to find the specific items that are out there in the wild. Of course, that also works indoors. We've just done it outdoors because it's slightly more interesting, if you want. What we see here on the right is also this sort of then autonomously exploring this. So rather than steering it around, or we've seen this kind of drone being flown around, if you've got a large environment and you actually need to explore it, you want to have a robot that does it all by itself. And so we've done a lot of work in that context, which is called next best sense planning. Really, we're trying to optimize where these robots go in order then to come back with the highest fidelity overall radiation, which will then inform the next step of where you go and what is the most important item that you then needs to pick up, sort away, and in order to eventually clear out an entire environment. Now, that doesn't have to be outdoors. As I said, this is often also indoors, and in particular when it comes to post-operational clean-out in nuclear domains, it's important particularly to be able to go about and basically put things in bins. Now, talking about putting things in bins, that's our next step. That's what we will be doing next. So we have got Soren here. You see him here on the right-hand side, the second person, and there's also some a mobile platform that can go about and can autonomously navigate in any environment, linked with teleoperation with haptic feedback. And we've done this sort of teleoperation within NCNR in different settings already. Here's one on the video where you can see one of our colleagues operating a haptic feedback device and then tidying up over a long distance where a secure link our lab effectively. So I'm going to take now my iPad and be able to show you around a bit more of what we're up to. All right, let me just disconnect this. I'm also going to change over my microphone. So hopefully you can hear me on that one now. And what we see, if we walk around a little bit. So give me a thumbs up, Peter, if you can hear. Yeah, you seem to hear this now, all right? Yeah, perfect. So here's our robotic platform. We've got a bin, we've got an arm, we've got an operator. Imagine this operator could also be sitting somewhere quite distant away. We're not showing this right now, but there's a lot of work also in augmented and virtual reality in order to provide a very immersive environment so that people can actually really over long distances see and be immersed into the operational environment where this robot is probably in an environment you don't really want to be at. So what we're going to do now is Soren is going to navigate the quite big platform, and which is currently, because we don't want to have any mess up with our Wi-Fi connected with wires here, and pick up this really dangerous item that you see down there. I'm not going to get close because it's virtually radioactive. All right, yeah, let's make the thing move. Yeah, let's get it moving. Of course, as you can already see in the background, there's also some strawberries, because just before we've done actually some strawberry picking with a similar setup here, where also this arm is being used. And now we can see Soren actually operating this Franca robot over there, basically using it as a very fanciful joystick, which gives him also force feedback. So he has a very dexterous ability to manipulate objects. So not just these kind of simple boxes as this one, but also can actually manipulate much more complicated objects and can actually feel what they are like. So that's one of the key ideas here. And we're also doing some work. You see these kind of nice markers on top of it, where we're doing some haptic guidance in order to, again, support the operator to really be guided towards this object so they can manipulate this. Right, the box is in the bin. That's the key bit that we have to achieve. And then, of course, the platform can carry on. And we can actually carry on also with this sort of mapping as we've seen before. Right? So now we have removed something. We can start mapping the environment again, in order to find the next best thing, or the next most important thing we need to actually look at. So that was a very quick run through. I give you a bit of a look around the whole sort of lab here. It's only one of a number of robotics labs we've got here. So there's also more fanciful teleoperation devices that one can work with. We have got quite a number of these setups of these Franca robots in order to do the sort of manipulation research also within NCNR. And you see this sort of setup is indeed a kind of a leader-follower setup, where indeed here can be an operator and we can really investigate how it would work if these people are long distances away. So that should give you a bit of an idea of what we're up to. Peter, anything?
Wonderful.
From your end you want to say?
Fantastic, Mark. Very nice. Good to see the robot doing what it's told to do, or autonomously doing what it's been programmed to do. I believe Tom Scott has joined us down below. See if we can just add him to the screen and say hello. Tom, can you unmute yourself?
Hello, everyone.
Oh, there
Hi,
he
Tom.
is. Hi.
I'm wearing my National Centre for Nuclear Robotics T-shirt today, because obviously this is all part of the NCNR programme, which has been a huge success, led by Rustam at the University of Birmingham. So I'm out in an event shelter at the University of Bristol's Fenswood Farm, which is a 245-acre facility just outside of Bristol. And at this facility, we have our nuclear robotics test facility. We have a menagerie of radioactive sources that we can use for testing devices. And today we are showing you, courtesy of Suresh, who had a picture there, we're showing you some of the detection capability that we've integrated with the DJI M300 drone system, which is their new emergency response drone from DJI. I'm just going to quickly show you. You can see behind me, this is the M300 system. And as part of what we've been doing, we've been integrating a sensor which is used for security and emergency response applications. This is a combined gamma spectrometer and a neutron detector at the same time. So it detects X-rays effectively, and it detects neutrons. So both of those things are important in case of a nuclear disaster, but they're also really important in case
point has been updated. Please check it on the
that's
map.
the drone talking to me. They're important in terms of if there was an incident, or if someone was smuggling radioactive stuff into the center of a city or another site, that we can use detection technology to detect the radiation, but it has to get close to the radiation source, and we ideally want to do that without people being involved, because you don't want people getting exposed to the radiation. So the system that we've developed just behind me, which will be flight testing as part of this demo, is designed specifically to map for radiation in the event of emergencies, and it's actually just been deployed at the NATO summit that we've just had over in Belgium, as an actively deployed technology that was basically used for security and surveillance whilst the summit was on. But it was used to fly around the building that the summit was going on and the nearby area to map for radiation and to make sure that there were no strong radiation sources either in the area or coming into the area whilst the summit was on, just to keep everyone safe. So the system is the first time that anyone has integrated a radiation mapping system with a DJI drone. Obviously, DJI is a Chinese drone manufacturer. And for this existing system, what we've developed is essentially a small robot which sits underneath and communicates via the Skyport hub to the drone, and all of the telemetry from the drone in terms of the radiation and also the height above ground data as well, which is recorded from a downwards facing LiDAR, is piped straight through the drone's transmission system and comes straight to the handset of the pilot. So this is the sort of handset. And for the DJI, you have two replica handsets, one for the pilot and one for the navigator. And Suresh, if I could just call you in. So I'm going to be flying using one handset, but Suresh will be using the navigator's handset hooked up with an iPad. I don't know if we can see here. You can see that on the iPad, we've got a map of the UK, and in fact, it will find where the system is, and it will zoom in and show us exactly where the drone is. And at the moment, the drone is in my event tent, and we're shielding it nicely, but it's just moved in. We can see we've got a spot on a map, and we can switch in our map between satellite. We can see this is the Fenswood main building, and we can swap to normal sort of Google map, if you like, to understand where we are. And as the drone flies around, we form a snail trail across the map, of which Peter's got videos of that maybe we'll show later, so that we can understand as the drone is traveling what the radiation levels are. And of course, if we fly the drone in a pattern, so a grid, then we can cover quite a large area effectively in terms of searching for radiation. And that has applications in nuclear site monitoring. It also has applications in mineral prospecting, looking for valuable things like gold, which is something I'd love to do when lockdown is eased and I can travel to other countries, to travel to Australia and see if I can go and find some gold in the desert using this exact system behind me. So Peter, I'm gonna hand back over to you for a minute, whilst I'm gonna just take the drone down and prep it for takeoff. Are you there, Peter?
I am here. Sorry, I was trying to share your video whilst you do that. That's wonderful. Okay, can you answer questions whilst you set up at all, Tom?
I can. Well, Suresh, if you wouldn't mind putting the drone out to the side, and we'll get ready for that. Yeah, please fire away with questions, Peter.
So we just have one question, which is how far away can you be from the drone?
We can be as far away as the DJI telemetry system allows. So there's obviously, depending on the country, there are laws as to how far away the drone can fly from you. In the UK, we have to stay within line of sight, which is about 500 meters. But in reality, the drone can send its data over about 5 to 7 kilometers, which is a lot further than I can see the drone system for. And of course, in the event of a nuclear emergency, I want to fly the drone beyond line of sight, because if I'm in sight of the nuclear accident, I'm probably in danger. So yeah, good question.
Yes, you don't want to be quite that far away or too close. There's definitely a sweet spot.
Something that we've done through the NCNR grant is we've taken this technology actually on a fixed wing drone system, and we've mapped 16 square kilometers of the land around the Chernobyl power plant. And in doing so, we have gone beyond line of sight, and we've shown that in the event of a real emergency, we now have that capability to be able to do that. Now, obviously, that was in a different country where the rules are different for flying, and that was permissible there. And we hope that in the near future, that out of line of sight flying for nuclear emergency response applications would be just as allowable in the UK. And we use sites like Fenswood where we can fly out of line of sight, certainly a big enough site. It's testbed sites like this which allow us to prove to regulators that we can do it safely. Good. So Peter's actually showing you on the video, which was very helpful, the kind of snail trail data that we've got coming in from the system. So this system is transmitting at a 1 Hertz rate. So we're getting in radiation data every second from the system, and it provides us with information around the intensity of the radiation. And obviously, essentially a snail trail is lots of point measurements made one after another. So as we fly the system around, in fact, usually we fly it completely autonomously, so that all we'd be doing is sitting and watching the incoming data. We can see the data as it's formed as a map, and you can see there's a hotspot somewhere in the middle of that map that's showing there on the screen. And what we can then do is, once we've seen a hotspot, we can send the drone in, and we can go slower and we can go lower, and that helps to refine exactly where the hotspot is located. So once you've got to that, you can then switch to the thermal imaging capability, which is a different wavelength of radiation effectively, and you can start to correlate whether that radiation hotspot matches with a particular object or feature that's on the ground. And of course, in the instance that we're showing you here, what we can see is a metal ammo box, which is actually filled with rocks which have been collected from parts of the UK, which are naturally radioactive. So this is not a strong radiation source, but it's strong enough that our system can detect it quite easily. And of course, when you switch to thermal imaging, it sticks out like a sore thumb because it's a metal box in a big grassy field. You can't actually see it when it's out in the field because the grass is too high. But of course, when you fly a drone directly over it, you can of course see that, not only in thermal, but with the HD imaging capability. And there's 3 cameras on the system when we fly it, and you can switch between them intuitively as you want as the pilot, which is really good. So once you've found a radiation source on the ground using this technology, then it's actually convey those coordinates to Mark, for example, to send in a ground robot, which would then go and investigate in much more detail and potentially take the object away and do something with it safely.
Wonderful. Thank you, Tom. Right, I'm going to leave you alone for 10 minutes so you can go set up. And I'm going to see if just have a chat to Mark. Hi, Mark.
Hello again.
Okay, so that went quite well. That your demo worked very, very well. So I think the same question applies to you as well. Is how far away can you be from your robot, and what problems does that actually cause you?
Yeah, it's the question of actually communication range in that sense. So there's two answers to that. On the one hand, we operate robots autonomously out there in the field almost all the time in have a test bed 4.5G to actually see what sort of high bandwidth operations we can do. So we regularly operate robots from here that are actually about 100 miles away. So that's not so much the problem for these autonomous robots. Of course, if there is indeed a nuclear disaster of some sort, that could well have massive impact also on the communication infrastructure and interference you would have on site. So that's when it really becomes important that you don't just have teleoperation, but you also have autonomy. And that's where, if you have seen these sort of things before, where you need to autonomously explore an environment in order to then also be able to know where you may have higher levels of radiation, which prevent any direct or good communication, and to go somewhere else in order to overcome that.
That's a very good point. So you say autonomy, and when you say autonomy, it doesn't already know what it has to do, but it has to work out its own route and make its own decisions based on some form of form of decision-making algorithm that you've written? How would that work?
Yeah, so there's different aspects to it. On the one hand, if you're really going in a completely unknown environment, we've been early on in NCNR, we've been looking at terrain assessment, so traversability, where can you actually go, which are the routes that are traversable by a platform like the one that we've seen behind. That's a bit more difficult, in particular when you are in an environment which may have undergone quite some significant change because of some disaster, or just because you're in an area that nobody has ever been in for a very, very long time. So so that's important that you actually use the sensors, you know, any sort of 3D sensors you may have on there, to build a map of the environment to then be able to identify the path that you can actually traverse. Then the next question is, which is the next place that you want to go to? So identifying exactly what is the area that I have not yet explored, and which potentially gives me some new information so that I can build up an actual information map over time. And that's something that our colleague Ricardo has also been working on. He calls this next best sense, and actually takes multiple criteria into account. So it's not only about basically finding a particular object in there, so like a radioactive probe or something like this, but also different criteria. Of course, we could embed into that you want to, on the one hand, find radioactive sources, but you can also try to model to get not too close to them at the same time, while you're also trying to complete the overall map.
Wonderful. I can see Tom setting up here, and so do you feel in the future that these systems will work alongside each other? So Tom's technology with the drone will be able to find radiation sources, and you'd be able to send in ground vehicles to go and interact with those radiation sources.
Yeah, of course. That is I think one of the key bits, and so you see more and more of these sort of systems approaches, where a drone has clear benefits when it comes outdoors, and we can get a initially probably relatively coarse overview map, but it highlights. You can even start building an a priori map of the environment that you then refine by actually going into that. There is no real problem in order to bring this together, other than at the moment, due to we all know the challenges that we face at this current time, that we just haven't been able to share the same environment and actually tried it out on the same place.
Wonderful. Yes, the pandemic's definitely put a bit of a dampener on these sorts of things. Hi, Tom. I can see you up in
Hello,
there.
Pete. I feel like I'm a sort of BBC broadcast journalist right now, because you've probably got the background noise of the drone. You can hear it's quite an angry bird.
Yes.
And hopefully you can see just up in the air, we've got a full HD camera gimbal payload, which is the thermal imaging, and then we've also got the radiation mapping system, which just sits just underneath here on this side. Now that's transmitting its data live, and really importantly for mapping radiation, it's got a downwards facing ranging LiDAR with 120 meters of range, which allows us to get height above ground. And that allows us to calculate the on-the-ground radiation from up in the air, which is really very important. And if Suresh just shares the screen from the Navigators app, you'll be able to see that we started to form a snail trail. I'm just going to hold it up, which hopefully you can see. There we go. Maybe we'll get a bit closer. Can you see that okay?
Just about, yeah, we can just see the little loop of the track.
And now the important thing there is that's tracking exactly where the drone is at any one point in time, and you can see that there's a color that's proportional to the counts. Now the counts at the moment are really very low, and that's good because I'm not expecting a big radiation spike today. But of course what the system does is it auto scales, so if I did encounter something that was really radioactive versus the natural background, it would very quickly scale that for me and show it as a nice bright red dot, whereas all the other points would be green. We're at a count rate of about 81 counts per second, which is, trust me, it's normal for Bristol. Bristol's not that radioactive. But typically when we're flying at Chernobyl, we're talking of thousands of counts or tens of thousands of counts per second. And it's really very obvious. But yeah, this is the drone system. You can hear it's quite noisy, as it should be. And I'm going to just take it off for a little bit of a test flight now, take it out over the fields.
So one last question just from the previous session. Just before we start this next demo with you, Tom, how does weather affect you? Because we've got a comment saying beautiful day for drone flying. What is your limitations? Is there a limitation on wind speed or rain? Do you have an IP rating? Can you take rain?
There is, and I've moved the drone away so you can hear me a bit better.
No, we can hear you quite well, actually.
All right. Essentially, it's an aerial park at the moment, which is quite a nice place for it to be. And it will stay up for about 55 minutes for this platform. This platform is specifically created for emergency response applications. So it has an IP rating, which allows it to fly in the rain, which is great. And it can fly in reasonably high winds, but not sort of tornado force winds, but sort of wind speeds of around 15, maybe 20 miles per hour. It can cope reasonably well. And that's because it's quite a big, heavy, powerful system. And certainly a lighter be able to sort of do this. So that's the reason why we've selected this platform specifically to integrate with, because it, versus any other drone system, really it has the best capability for flying on most days, not all days, but many more days than you could for most other drone systems, certainly.
Okay. Thank you, Tom. I'm just going to reintroduce everybody because our live streams run every 30 minutes. So there may be a new group of people who are joining right now. So first of all, my name's Peter. I'm based here at the University of Birmingham, and I'm basically acting like I'm a base operator that's overviewing work that's happening out there in a nuclear reactive site or a nuclear disaster site, where we're going to send a drone to investigate, to find a radiation source. And then in a separate lab in Lincoln, we're going to actually approach that radiation source using a mobile robot. So first of all, I'm just going to introduce Professor Mark Hanheider.
Hello. Hello, everybody.
Hi, Mark. So Mark is based at Lincoln, where he'll be operating his vehicle, and he'll tell you about that in a moment. And also Tom Scott is Professor Tom Scott, who's in a field in Bristol flying his drone. So since Tom is up in the air and we've planned for Tom to start, I'm going to switch over to Tom.
I really envy Tom. I really envy Tom being out there. It's much nicer.
when we practiced this before, the weather was horrible. So,
but now I envy you.
Lady Luck's been smiling on us today. So I'm actually just going to bring the drone over for us a second. And Pete, just tell me if the sound gets really terrible as it gets closer, because I want to avoid that. Hopefully you can see the drone coming in just behind me now. I'm technically flying it backwards. So hopefully you can see this is the drone system that we've been working with. It's a DJI M300 system, which is an emergency response drone. And it's not quite an all-weather drone, but it certainly is weatherproof. It's able to fly in the rain and in reasonably high wind conditions. And this is why we've chosen to work with it. And what we've done for the first time is we've integrated a radiation mapping payload into it, but it's essentially a radiation mapping robot sensor, which is fully integrated with the drone. So it takes power from the drone and it redirects all of its telemetry in terms of radiation data and its height above ground, because it's got a ranging LiDAR, and it pushes that through the drone's communication system straight to my handset and to the navigator's handset, which is an exact replica. I'm just going to swap over. And what it does is it then, by sending that data in real time at a 1 Hertz rate, we're able to then plot that data. If I sort of zoom in here, we're able to plot that data, as you can see, on using an app that we've developed by essentially partnering with DJI and Apple. So we can see that data in real time. And I can also share that data with other users who have got clearance to be able to see it. So what that means is I can take my drone up, either for routine monitoring of a nuclear site or in the event of an emergency, and I can fly it around. I can do it manually like I'm doing today. I'm just going to send it off because the noise is, for me, really annoying. And I'm just going to put it into an aerial park a short distance away, so it's safe. Now, the flight time on this is 55 minutes, so I can leave it in the air for ages whilst I'm talking to you. But usually for surveys, we do these automatically. So the robot, which has collision avoidance built into it, will execute a mission which follows a series of GPS sort of waypoints in order to essentially make a sort of grid pattern or a snake-like trail to cover an area of ground. And as it does so, it's recording the radiation at 1 Hertz rate, and therefore recording a series of points. And those points are projected onto a map using our software. And with that map, we can also combine the height above ground data And that allows us to calculate the on-the-ground radioactivity, which is the thing that the people really want to know, because it's about people on the ground being exposed to dangerous levels of radioactivity. So it tends to be that the radioactivity is much less when you go up to a high altitude than it is on the ground, because you get some natural gammas coming off the ground. And for this particular system that we're flying today, we're actually not only mapping the gamma radiation, which you can think of as being like the X-ray radiation, we're also mapping neutron radiation. And the sensor that we have inside is actually a sensor developed by a company called Chromec, which is a combined neutron and gamma spectrometer. So this gives us exactly the type of information that we need in the event of a nuclear disaster. And indeed, this technology usually is carried by emergency response workers, and they would wear it. But of course, in a real nuclear incident, you don't want people being exposed to dangerous radioactivity. And hence we've got the drone system to do this instead. And the drone system in the UK, I have to stay within line of sight, so I could fly it up to about 500 meters away, and then I'm struggling to see it. But its actual capability is it can fly up to something like 5 or 7 kilometers away, so well beyond line of sight. But I've still got full real-time control over it and full real-time transmission of data back to myself and back to my navigator. And that's really very useful to be able to do that because it's about real-time situational awareness. And of course, the map that I collect, and Peter will be showing a video in a second, I'm sure, that map that I collect, I can share with other first responders. And if I'm sharing with Mark, I can show him exactly where any hotspots I've located are to be found. And with that information, he can send in a robot on the ground to track it down and potentially either pick up the object or cover it with something else, and to do the really dangerous bit, actually. So the robot is used as a sort of search and find mission, a bit like sending out a dog on a mountainside to look for people who might be injured. And you can see this sort of snail trail of data that's produced live off the system. It's coloured so that essentially red areas would be really, really high radiation, green areas would be really low. But for this map, you can see the system is scaling itself. So when we find an area which is hotter, that comes out as a redder colour. When it's yellow or orange, it's a lower colour. And what we've got here in the map that's being recorded is a really, because we've used natural radioactive rocks from a part of the UK. But you can see on the map, you've got your hotspot there. And once you've found it, then what you can do is you take the drone in low and you take it in slow. And then that allows you to get an even better handle on exactly where it is. And that would be the point in the mission, and you can see the data's honing in on that now, that we would switch to one of the other cameras, and we switch to the thermal camera, which is on board. And the thermal camera is obviously imaging heat. And so by using that thermal camera, we can correlate the hotspot we're detecting for gamma radiation with a physical object or a feature on the ground. So that could be a building, or that could be, in the case of this demonstration, it's an aluminium ammo box, which has got the radioactive sources inside. And you can see this is stood out in a field of wheat, where the actual wheat is sitting higher than the box. So I can't see the hidden source. I have no clue where it is, in fact, because we hit it blind for this demonstration. But once I've got the drone over the hotspot, of course, it's really obvious to see with a thermal camera, and you get in really close and eyeball it, both with the thermal camera but also with a normal HD gimbal camera, which is coincident with that. And you can see, hey, this is a metal box. And so with that information, the location and the specific object that we're looking for, that's exactly the information that we then hand over to Mark, and then he would send in his robots on the ground, and our job is complete.
Wonderful. Thank you, Tom. I've got one question that's a very interesting question. Are you looking to expand this system to allow multiple drone robots to survey the same area at once? So can you send out a swarm of drones to survey a larger area?
You can indeed. That's something that we're working on. Another platform which this system works on is the DJI M100, which is a developer platform where we can use, for example, ROS, and we can coordinate a drone swarm quite happily with multiple units. So in fact, what we've done in terms of making this system is we've actually made 5 mapping systems, so we can go on 5 drones simultaneously with all of the data feeding back essentially onto the same navigator app, so that you can have one supervisor, if you like, seeing all the data in 5 different systems. And of course, the benefit of having 5 is you can cover a large amount of ground much faster. Yeah. And so you can do things more quickly, you can respond to the emergency faster, and hopefully make the right decisions quickly too.
Wonderful. Thank you very much, Tom. So I'm going to pass it over to Mark. As you say, that these two systems do cross over theoretically, and hopefully one day we'll see that when pandemic restrictions allow. Hi again, Mark.
Hi there. Thank you, Tom. That was very nice handing over indeed. Shall I go, Peter? Yes, well, let's get started.
Yes.
So maybe Peter can quickly share also some quick overview slides, because I want to just give you a bit of an idea of how this link works. Now we get a map, and this is kind of probably not a very detailed map of an environment, but we've got a kind of big overview. And now Tom has pointed out, the drone has pointed out where we might actually want to go and retrieve an object, secure it effectively. And so our work in NCNR is bringing together mobility on a mobile platform like the one that you see right there behind me, which is actually capable of going outdoors, and we actually use that a lot in also our agricultural applications. So this is really something that can go in a wheat field like Thomas just shown you, and then it's equipped with a manipulator. You see there at the moment, that one is not quite ready for outdoors, but we've got a number that we can also use outdoors. One of the reasons we were not as brave as Tom, really, so we stuck indoors for today to give you a little bit of a demo. And we've got another robot on that side. You can probably see that just there. There's one of the operators, because the vision is now where we can very easily navigate outdoors. We've got lots of capacity there, even in unknown environments, build them up and find our path in there. Once it comes down to the actual handling the object, inspecting it close, you want to get an expert operator like this guy in the loop to actually work in there. So with all that said, we are not usually working so much with the actual radioactive drones, but we've done a lot of work also to close this loop between simulation and reality. And here's actually the idea that what Tom has shown you, this sort of map we get there, we can also replicate in our system to then do autonomous exploration in such a kind of a priori given map, for instance. So what we see here is actually real a run in our farm environment, not wheat, another farm, effectively, and having it linked to a simulated environment where we also put one of those sources. We don't have to put the box in reality because we've got a digital twin. We can actually do all the algorithmic development in that one without actually having to find radioactive rocks that we put somewhere in the field. So it helps us really with the development. But in the end, you could also have this sort of fully autonomous exploration. While you saw Tom going about navigating and flying the drone in a kind of fixed pattern, what we're also interested in is autonomously finding out the right places where the robot should go next in order to optimize and fully autonomously, if you don't have to have full control, you want to be far away from where it is, to actually build these sort of maps and the robot deciding where it needs to explore, where it needs to put some information in. Now, once we have found that sort of radioactive source, or maybe even a couple of them, then of course we want to come in and send the platform over there, and that's what we're hopefully going to show you a little bit live. And it brings really together the idea of navigating a mobile platform like the Thorwald robot we've got here, and then starting manipulating objects with teleoperation, where we have an expert, a human in the loop. And you see here on this video that one of our colleagues is operating our lab robot that is right next to me from his home, very much COVID pandemic-like. He's got a haptic device and can actually tidy up our lab from his home. And it's pretty much the same sort of setup that we want in the nuclear industry, right? You're going to be safe, stay out of any harm's way, and still have the dexterity with haptic feedback with an immersion operation in there to be able to do your job effectively. All right, I'm going to switch over to my iPad now and give you a bit of a view of the overall lab space here. Bear with me, a bit of a swap. You can still hear me?
Yeah, so Tom's going to take, Mark's going to take you mobily around the lab.
So we're going to have a bit of a look around. This is the platform. Also, as you see, we've got a lot of crossover between what we're doing within the National Center for Nuclear Robotics and our other main domain, which is agriculture. So the very similar platform, as you see here, has just been picking the strawberries here yesterday. So there's a lot of links between these different
operations, because also there's the same challenge of being able to autonomously navigate outdoors and then manipulating potentially quite delicate objects. Right, what Soren is going to do, he's going to make the robot move and pick up this item here that you must imagine for now that indeed Tom has discovered and has told us roughly that it is somewhere there. So then we need to be able to perceive it and eventually have it manipulate. So let's make the big platform move.
Just before you pick it up, Tom and Mark, do you think you could show us somebody moving the arm just to show how the arm?
We'll show you moving the arm in the section. So, you know, first step is always that we get the base close, and then the idea is really here. So here you see Soren actually using a Franca robot that is here and using it as the immediate mirror of this setup. And what this direct mirror basically allows, that he can actually operate and use this Franca as a fanciful joystick that gives him also haptic feedback, so he can feel whether he's actually hitting something, whether he's grabbing something, and that gives him a much more dexterous and immersive experience in order to be able to manipulate objects that are not quite as nice as this one. The key aspect here is also that we use also haptic feedback, not only directly from the physical world, we can also generate virtual forces. By knowing where the object is being directed to it, the operator can feel also to be guided towards picking up these sort of objects. So we have now done our main job. We have tidied it up. We can carry on and go to our next place to select the next one. Now, as I said, this platform is really just for practical. You can take the very same system as it is and take it outdoors for to have the direct link to what Tom has been showing before. And the sort of type of maps that we get from this, these sort of radiation maps, which give you, basically it's a heat map. It's the same sort of maps that comes from Tom's system as comes from our autonomous radiation mapping system, where we have done this in this digital twin, as you've seen before. So immediate link, that's one of our ambitions that we're going to go further to basically present you as we move forward with our developments as a much more integrated system, where indeed we bring together drones that provide us with an overview. They can provide us with an initial map that also can help facilitating in challenging environments, and then bring it in with the autonomous navigation capabilities and the sort of haptic teleoperation that we're doing here at Lincoln.
Fantastic. Wonderful. Thank you, Mark. And that's a fantastic looking robot though, isn't it? I mean, it just looks like it's very capable to go off-road and really go outside of the lab.
Yes, it definitely can. As we used this in many different environments already. It can conquer our Lincolnshire muddy fields and also the sort of steep inclines we are facing. So together with some algorithmic development about terrain assessment, to be able to actually assess which routes, which parts of a map you can traverse with such a robot, that allows you to then also go into unknown environments, right? We're building the map and on the go, and can also navigate certain challenging environments that may actually be the result of some disaster and not just a nice wheat field as we've seen.
Okay, I've got one rather technical question in the comments. So I think we have a robot researcher here. He said the simulator looks very nice. Just wondering how the radioactive sources were modelled in Gazebo. So Gazebo, to those who don't know, is the simulation package, and I believe that's part of the robot operating system. Mark, how did you model the radiation sources?
Oh, I can refer to my colleague Ricardo if he is on the call. But in general, there's a really nice plugin that has been developed to simulate radiation sources as a plugin within Gazebo, and you basically just put it there, and it models the physics of such a radiation source, also taking some of the physical properties like obstacles, etc., into account.
Ricardo, would you like to comment on that?
Yeah, thank you for the question. I'm actually not the developer of the plugin. We were helped by the partners of the physics department. What I can say is that the radiation source is modeled as a pointwise source which emit constant activity and the intensity of the radiation scales down based on the distance. So there's not much more details that I can add because I was not the first person involved in the development of the Gazebo plugin.
Yeah, but the nice thing is that we basically brought it together, so we can we can just augment our real world with these virtual objects, and the entire robotic system can work the same.
Wonderful. Well, we've got about 10 more minutes until the next demonstration. So if there's any more questions, feel free to stick them down there in the comments. I've got a similar question for Tom and Mark. Is that during this pandemic, what did you do when you couldn't get into the labs? What did you do when instead of doing these live tests and experiments?
Tearing my hair out.
Yeah, it's all gone. It's all gone. But I mean, COVID's been a real challenge, but what it has taught us is that we can achieve a lot by using, Zoom, Teams, whatever the platform, and that you can do virtual hackathons in many ways. We've been fortunate in that we have an outdoors facility and capability, which has meant that we've been able to, certainly with development of this, being able to quickly get things out into the field, either on your own or in a socially distanced pair to do the necessary testing and development. But one of the first things I did within lockdown was to get my team and myself to get all of our sort of electronics kit to people's houses, and things like 3D printers, set up a 3D printer in my study so that we could go through the stages of rapid sort of iterative prototyping very easily without having to be in a university lab. So, some of it we literally had to sort of work out as we went along. But I think we've all achieved within the consortium a lot more than we thought we could, given it was a global pandemic.
Yeah, indeed. I mean, we're also lucky in that sense that we've got quite vast outdoor spaces on our campus that we could do some of the outdoor bits in robotics. But indeed, the development of digital twins and simulations has advanced significantly over that time. And that does pay back to some extent. We didn't have that technology initially because, of course, people find it much more exciting to get on their hands on the real robots. But in order to actually, allow also students to be educated in it, we make much use of simulations, much more use of simulation than we did before. Because all of a sudden now you see how this scales, right? It's much easier to run 100 simulations to educate people in than actually getting 100 robots to operate. It's very windy there, Tom. It's very windy.
Yeah, it is. It's
Oh, now you're muted.
Yeah, as Peter said before, one of the questions is how high a wind speed can the drone fly at? Today's wind, I think, probably is something like 15 miles an hour. It's absolutely fine in these kind of wind speeds. It will go up to much higher wind speeds as well. So, although it sounds windy, it's perfectly all right for drone flying.
Right. Thank you, Tom. I'm going to leave you for the next 10 minutes to set up again and see if you can get back up in the air, and we'll come back to you at 5 o'clock. Thank you, Tom. Thank you, Ricardo, for the good answer on the gazebo simulation. Okay, a bit quieter now without all that wind noise. I'm just going to ask you the same question, Mark. Tom's drone is designed for disaster response or emergency response, which means that it is IP rated, which means that it can fly in the rain and certain amount of wind. What can your vehicle do? Can you drive around in the rain, or is there certain parts of it that are more vulnerable than others?
Certainly, there are parts that are more vulnerable than others. So the base platform, which I said we use a lot in also all our agricultural applications, from crop care to actual harvesting and logistics out there. So that one has proven itself in the rain and in all weathers, so we haven't got any problem with that one. The manipulation part of it, so the Franker arm that you see right there on top of it, that one is the one that hasn't got the full IP rating. So, which is one of the reasons why we wouldn't go outdoors with that. But it's a research project, right? So if we actually are developing this further, for actual deployment outdoors, we've got a number of other arms that we can use for that sort of application. And we also got Also, when you move forward other haptic devices, then just using one of the Franker's defensible joystick, I can give you a quick look. So there's other haptic devices that we can use, which are quite familiar probably to people that have worked on sort of haptic teleoperation. So there's other platforms that one can easily use. So that we're quite flexible in all the algorithmic work, I would say, is not really bound to one specific robot platform. So again, sort of, taking fruit picking there. We've done that with 3 different arms now, depending a little bit on the sort of setup and application we do. Well, you still have the same sort of algorithmic background.
Thank you very much. We've got another great question, actually, which is when you're teleoperating this vehicle, or the vehicle is working autonomously and you're teleoperating that autonomous action, what happens when you lose communication? When you lose communication, does it just go mad and start driving into a wall and smashing everything up, or is there some fallback operation that's in place?
Right. So obviously, when it comes to navigation outdoors, all of the, let's say, obstacle avoidance, all the safety bits are on the platform itself. So it can navigate even if it has no connection. And a lot of the work we're doing is about autonomous operation. We've been sending out these robots far away into fields where they lose contact to the probably only 2G network ever so often, and they still do their jobs in there. So in terms of navigation, that's relatively easy. What you lose if you lose connectivity and communication breaks down is at the moment, the teleoperation part, right, where you want to actually have a very, very low latency communication between your operator that sits there. Can't do this properly. There we go. and the arm. So that is a functionality that would break down as it is at the moment. We've got within NCNR also people that work particular on resilient electronics. So that look at the aspects there, how you can actually make electronics that are resilient even to high levels of radiation. That is something that if you want to really go out with something like this, then you need to work on that. That said, while teleoperation and shared autonomy teleoperation is brilliant and is actually something that the nuclear sector is extremely interested in because they really want to have the operator in the loop, a lot of the competence to actually do autonomous grasping has also been developed within the context of NCNR, mostly also to actually support the operators in it, so to guide them. So, if you're going to do something like shared autonomy and you want to guide a person operating a robot remotely towards an object, you already need to understand of how you want to grasp it. You need to actually have planned for the trajectory to then use that information to guide people. So in that sense, it's quite... In some ways, it's often easier for us to say, like, we're just going to do autonomous grasping of these sort of objects. It becomes tricky if you've got objects that are very, very odd-shaped, very strange physical properties, extremely unknown, and that's where some of the kind of fully autonomous grasping challenges come into the play. So I can give you another kind of, we've just inspired by the strawberries right there. Is this sort of, if you have them and in growing in bunches and you want to pick one specific one out, you need to push the others away. And that's another sort of extreme challenge you also face if you have a heap of nuclear waste that you need to sort out. So that's why we've done a lot of work also to learn how you actually can push a heap of bits autonomously out of one another. So you learn how to actually segregate this so that you can see the individual objects and then you can pick them autonomously. So you can do those sort of things in communication failure. It certainly won't go mad and won't crash into things. That's not going to happen. But indeed, low latency, high bandwidth teleoperation, fully immersive with an operator 1,000 miles away is going to suffer.
Yeah, and a very, very good point. And I think the point you made is that this is research technology. So Professor Mark Anheider and Professor Tom Scott and all the other professors and researchers within the National Centre for Nuclear Robotics, they are working at the cutting edge of what's possible. So not always is it reliable, not always is the system fully built as perfectly as you might expect to see. But what we're doing, is proving that through their advanced algorithms, vision systems, control systems, network communications, that we're actually pushing the boundaries of what's actually possible. And then the hope is that companies and industry take that technology and run with it and actually build it into a product that's actually retailable. Now, again, thank you, Mark. Very, very well put. I don't know if Tom is back. Tom, can you hear us at all? Okay, I can't hear Tom at the moment. So what I'm going to do? Oh, there he is. He's back.
I am back, Pete. So are we on the next shift? Have we got new people?
Yes. So if you're able to start, if not, we can delay a little bit.
I will just quickly take off.
Okay, wonderful. Okay, so for those that have just joined, my name is Peter. I'm at the University of Birmingham, and we are all part of the National Centre for Nuclear Robotics, where we have 12 consortium universities. 2 of those universities are Bristol and Lincoln, and to the left of me here, or right of me, you can see Professor Tom Scott, who's out in a field with his large-scale drone, which has a radiation sensing device on there. I'm just going to mute Tom for a moment. Okay, so Tom has a radiation device attached to the bottom of his drone, so he will be able to fly around and search for a radiation source. So, for example, if there's a nuclear disaster or if there's a component that we're trying to locate, then Professor Tom Scott can take his drone out and locate that radiation. And then the idea is that we can then send in ground vehicles, which would be controlled by Lincoln. I'll just show you a little view here. So here's the drone below me, vehicle. Thank you, Mark. So Mark will talk to you about that in a moment. Hopefully Tom has took off now and I can bring Tom back in. And I'm here, as I say, like an operator that's overviewing all of the feeds from different vehicle operators to try and add some safety to the operation. Tom, I can see you're in the air again.
I'm in the air again. Hopefully the sound's not too bad.
Wonderful.
right by this here, you can see there's a slightly angry drone system, which is just behind me. I'll just move it another way. This is all in reverse as I look at the screen.
Okay. So that's some fancy flying because he's flying in reverse and then on a screen in reverse as well.
Exactly. So the system I've got behind me is a DJI M300 drone developed specifically for emergency response and with a very long flight time, so about 55 minutes flight time in good weather conditions. It's just an aerial park behind me. And on the bottom of that system, you can hopefully just make out we've got a camera, which is an HD video and thermal camera. And then next to it is our radiation mapping payload, just above my finger there. And that's a combined gamma spectrometer and neutron detector controlled by a microcontroller. And it's fully integrated to the DJI system through what they call the Skyport connection, such that we're taking power off the drone. And we are also putting all of the radiation data, as well as height above ground data. There's a ranging LiDAR on the bottom with a range of 120 meters. And it's forwarding all of that data through the drone's telemetry and communication system, such that the telemetry comes to the handset of the pilot, so it comes to myself. And on the handset, I can see in real time the radiation data. I can see the counts per second for gamma, counts per second for neutron. And I can also get a live video stream from the bottom of the payload, which looks straight down. And I can get the height above data, height above ground data at the same time. Now, my navigator also has one of these, but actually it's connected up to an iPad through their system. And on that iPad, I'm just going to let Suresh take my pilot's control a second. So he's in charge of the robot. He can actually see it, whereas I've got my back to it. And what we can see is on the live display is that we get a map that comes up and it transfers, if you can just make that out. And Peter will start playing the video in a second to show it as well. We get a satellite sort of base map, which is also a sort of normal Google map. You can switch between the two. And as the drone flies, either piloted manually or autonomously, it records point after point at a 1 Hertz rate, the radiation intensity and the energy. And then we put that together during a survey to form a map where you've essentially formed a heat map, as Mark termed it earlier, which is a really good term for it, where the reds are the higher activities and the yellows and the greens are lower activity. And you can see here in this inset video, which is sped up slightly, so we've got the time for it, that the color is auto scaled, so that when you come across something which is hotter than what we call background, you can see that all scales, the background color drops to yellow, and the little hotspot, which is a weak one created by some rocks that we've brought in, which are naturally radioactive, you can see as a red area, which is sort of right in the middle of the mapping zone as the map is conducted. So what that allows us to do is we can identify a hotspot from the data, and we can interpolate this data to form a nice map, color map across the whole area. But we can take the drone to where we see the hotspot. We can do that in real time. So the decision making is in real time. And then we can start to correlate that hotspot by turning and using thermal cameras to correlate that with any physical objects or structures on the ground, which might be what we regard as threat objects, but the radioactive object. And so in doing so, we can get in close. And in this example, we've got our radioactive rock stored in a metal ammo box. And it's hidden out in a field where the grass is higher than the ammo box. So I can't actually see where it is from my current position because the grass is too high. So it's effectively blind hidden for the test that we've done. But of course, when we get over it from the radiation data, we then switch on the thermal camera and we can very quickly see that it's a foreign object. And we know not only its radioactivity, we know its location, we know what type of object it is. And that's really important because then we can hand that data in real time over to Mark and his team, and they would then be able to take a robot out on the ground, which is capable of manipulating that object and ideally sort of taking it away and putting it somewhere safe so that nobody gets in harm's way from the radiation. So this is our sort of part of the project where we're using drones for reconnaissance, for finding hazardous radiation anomalies. And it's that data, which is importantly in real time, that we can share via the application with anyone who's got clearance to see the data. So what that means is if we wanted to, someone in central London could see the data as it's being recorded. And in fact, this system has just actually been deployed for real at the NATO meeting in Brussels, where it's been used to survey around the NATO meeting buildings to make sure that there was no anomalous hotspot activity and everyone was safe. So Peter, you're probably dying to put me on mute now because the noise is quite high in the background. Just like to say thank you very much, everyone, for listening, and I'm happy to answer questions in a second. I'm just going to put the drone further away.
And you hear me now? Yeah, sorry, I was having a few little audio issues there. Okay, wonderful. Thank you very much, Tom. Sorry, my computer's just slowing down. I'm going to just pass over to Mark in the hope that I can
I'll just take over. Brilliant. Thanks, Tom. I mean, I think it gives you a good idea of what sort of robots can already do outdoors and what sort of maps they can create by just flying around. And then, of course, the challenge comes, how do we link that and how do we use that in order to resolve the situation? Right? A drone has limited payload, even though it's a very impressive one. If we actually wanted to go in and dig something out, that's maybe when platforms like this one come into the play. Now, Peter, I don't know how much control you have regained over your...
Hopefully I'm back. Hopefully I'm back.
Right, okay. So if you want to quickly share my little bit of slide here, then I'll give you all a quick run through what you can then do following on from that. So really, I'm going to keep it relatively brief, but we are also interested in outdoors, and that's where the link also with Tom comes in within the National Center for Nuclear Robotics here. We do a lot of outdoor robotics also with robots going a lot in agricultural settings. So out there in the sort of wheat fields, Tom has also just shown you. And that's why we've done a lot of autonomous navigation, and we've been working a lot to make these robots work on their own for like hours on end, being quite far away. So, and this is an expertise that also comes in here, right? So we've just talked about a robot being probably, somebody in London being able to operate this. So long distance teleoperation or long distance autonomy is something that we're also quite interested in. So these platforms, what we see here is a kind of standard platform that we use for a number of operations, also within NCNR. And what we're interested in is taking the sort of data that Tom can give us and then working actually on the scene with a robot like the one we're just going to show you here. We've taken it inside, and one reason is that we were not quite as bold, and we were a bit aware of the weather could be changing, so we didn't want to go outside, because indeed one part of our robot isn't quite weatherproof yet, and that's the manipulation side. The rest of it can perfectly go out and sustain in the rain, and it does that a lot in other applications. What we're trying to do, and what we've been working on quite a bit, and also in response to the pandemic, and I think that's what you see with a number of robotics group, is to also invest a little bit in the development of digital twins. And I think that's an interesting development overall in response to pandemics, but also in order to boost development. And what you see here at the bottom is indeed a link between a robot that is actually going out in the real world, and then we have augmented the scene by linking in a digital twin that's basically a gazebo simulation that just replicates and takes the data from the real sensors and then can actually move in the virtual environment in a similar way. And we can just put a radioactive source like Tom has got in his field in there and do similar things like mapping environment, etc. And one of our focus areas was really to have autonomous systems mapping, so that they can go about and actually find the optimal path, let's say, to find the most information over a yet unknown environment. And that's one of the parts that we've done, what we call next best sense, to just send a mobile robot like this one around to produce a map that looks in the end relatively similar to what Tom can provide as well. And this sort of approach can, of course, be linked back into a drone. So we can also do the same sort of autonomous planning on a drone, but we can also directly equip it on one of our robots. And here we don't have the real sensors in here at the moment, but we can just use digital twins to actually emulate the same stuff and get qualitatively the same maps. Now, once we know where things are, we want to actually move over and do something in reality. And I'm going to just switch over to my iPad to give you a better view of what is actually happening. So bear with me a second. I'm going to also switch the mic so to be more mobile.
Right, I hope you can still hear me. Yeah, can you still hear me, Birmingham? Excellent.
Yeah, we can
still hear you.
If you can
put my slides back on as well, Peter, that would be helpful. Because what we see there is, on the one video here, is our colleague teleoperating one of these Franca robots remotely from his home, so over long distances, and we've had like encrypted channels so that you can actually have safe long distance teleoperation. We've also done some demos of that from London to actually operate in our lab, and here he's done it from his home to actually operate this particular robot over there. So we've done a lot of work in general teleoperation where we use a kind of symmetric setup, if you want, right? We have a robot like this one, a Franca robot, which is a compliant robot which has a lot of force sensing in it as well. So we can use that as a fanciful joystick to control this side. And having this mounted on a mobile platform is exactly the sort of setup that allows you to solve the problems that Tom was referring to, that you may be outdoors in an environment which is quite difficult to navigate because something may actually have happened in there, or in general it's challenging to navigate in. And then being able to pick up the nasty box, whatever that may be. Of course, this is a very simple one to set up, and I'm going to ask Soren now to actually start the robot moving about. Apologies for my very, very agile camera handling here. We're going to try to calm it a little bit now. So we see here this robot that is capable of really has proved its ability to navigate outdoors in many, many different applications, and weeks on weeks of autonomous operation. And here we then use the operator who's actually now in the loop. So we're not just doing autonomous grasping here, but he is actually using this to then be able to pick up the box accordingly. He's quite an experienced operator. We're trying to do a lot of research also to support operators in this, so that we don't just feed the same sort of angles that we've got on that setup there into this particular robot, but we provide force feedback so he can feel actually when he hits something. We provide force guidance, which means that the operator can feel the is dragged towards the object, if you want. Now, this is all very difficult to show you in in video. So that is something that hopefully, should we be able to host TAROS in real, and if you are somebody who wants to come to our TAROS conference in September, then you will have a chance to feel it, which is certainly much more exciting than just watching it. So that as an overall general kind of system, you can go from a reconnaissance mission on a drone, gives you an initial map. You can have a mobile platform that then has also radiation sensors on it and that can refine that map, approach the respective areas of concern, and actually start a tidying up mission. Now, it's not only in outdoors we're doing this. We're doing a lot of the, the nuclear industry has a lot of challenges, in particular also in indoors, where we have contaminated environments, and in particular of in situations where it's about decommissioning, so quite dated buildings and facilities that need to be taken apart. And in that particular domain, you really often have the problem that they have been, well, not been left in the best state for many, many years. They have been rotting away, and now you need to start tidying them up and start segregating and sorting different objects. A lot of waste that is not just actual nuclear materials, but it's just contaminated material that is about. And then you have a system that is more like the setup we've got here, where again we may have an operator who is at a safe distance from another cell in which we would put the objects, and then we have really the similar teleoperation setup here. We can even have a bimanual one where you've got two arms, and we've got a leader robot here and a follower robot over there, and the same sort of thing that we've just seen to actually operate on a mobile base, we can also do in on a kind of fixed base, where you basically start pushing objects that you may have put on this desk and try to sorting them into different boxes, depending on the sort of categorization of them. So see what type of radiation they are, what sort of material they are, in order to minimize the overall nuclear waste the high nuclear waste that you need to keep very, very safe and store for long periods of time. So that's a context overall in NCNR. As I said, there's a lot of overlap with the work that we're doing in agriculture as well. So we've got over there some strawberries. This particular robot has been engaged in doing some strawberry picking. Was it yesterday? Yes, it was yesterday. That's why this looks relatively empty already. So what we then do, similar platform, different manipulator, not just grasping, but snipping. And then you have similar challenges going out and about on your own, autonomously into the outdoors, where you have challenging navigation environments and having very, very dexterous specific manipulation. Of course, in picking, we don't do it by teleoperation. There it is actually autonomous. I'll finish here. I'll put my iPad back. I hope this is, nice view, very dynamic camera work here. I go back to my stationary place.
Wonderful. Thank you very much, Mark. I'm just going to turn off that camera and still put on this mic again. Fantastic, wonderful demo. So that's a very, very interesting point to actually talk about there, and that is that we develop many technologies throughout National Centre of Nuclear Robotics. We've published over 300 peer-reviewed papers, I believe, and the outcome of that isn't purely for nuclear. So we have the ability to pick up and assess and map and model lots of nuclear components that are either expired and need to go into waste, or new components. But these technologies translate across to other industry areas, such as agriculture. And Lincoln are leading at this, where they are able to do things like picking fruit from plants. And as Mark said earlier, it's not an easy task. Sometimes you need to move leaves out of the way. You have to be very delicate on the grasp and how you maneuver. So it's not a simple feat, is it, Mark?
Oh, no, not at all. As I always say this, we just do robotics in extreme environments. And I don't care whether that is, in that sense, nuclear or whether that is agriculture. Both are challenging environments, or to some extent extreme. So there's indeed a lot of transferable technology. So having said this about this kind of pushing leaves or other kind of fruits away to reach the one that you really want to pick is very similar to having a heap of nuclear waste and then actually planning to push things out of the way so you can grasp the one item that you need to put, that you'd actually want to get out of that heap to then put it in the specific bin. So that's why we've been doing a lot of just general fundamental research in abilities to sorting and segregation of quite cluttered, say, piles of objects you want. And whether that pile of objects is a big truss of strawberries or grapes, or is indeed contaminated objects that are lying around, is not so much a difference. You still have to kind of plan from an analysis of the scene and start segmenting it out. And so that's why we actually use a lot of the fundamental algorithmic work in different domains.
Just a question that came in the comments. I believe you answered it in the comments, but just for those that are listening to audio only or just watching the video, how long does your mobile platform actually run for? How far can it go, and how long can it go for?
It really depends on what you want to do. So when I said, I wrote in the comments 8 hours, and that is a mean value with a massive variation in it, because we use this platform, for instance, with our colleagues in something like UV treatment, high intensity light treatment of crops, and that high intensity light treatment means it takes just 2 kilowatts of light, just where the energy goes in that you can't run for 10 hours and the batteries are drained, but you can also just put more batteries on. So really scales. I would say our normal, when I say 8 hours, that is the kind of typical operation environment that you've got. If you do something that is high intensity work, like shining high intensity light or something, then you get less. If it's just moving in even terrain for a little bit, you can easily reach 60. And then it depends also on what sort of batteries you chuck in.
Well, unfortunately, we seem to have lost Professor Tom Scott at the moment, so I can't direct any questions towards Tom. So I'm sorry, Mark, I'll be asking you a couple more questions. One of the other questions to ask was, how does the remote operator get a sense of the environment that they're working in? So you had the operator there who was actually working line of sight, but how will they actually operate when they are remote?
Well, obviously, that's not the ideal situation, right? That's not the situation we wanted to have if indeed there were a nuclear source anywhere nearby. So we've done a lot of work in providing much immersive experiences for the operators as well. That can go from video streams that you actually just have 2 cameras that basically replicate your eyes in the scene, and then you get them directly fed into your eyes, such that they have a kind of stereoscopic view. Our colleagues in Bristol have also been working on that with us together. And then we go more towards also augmented reality, where we actually use the typical sensor we do for 3D mapping in robotics anyway. So we can actually reconstruct a scene in virtual or augmented reality and then overlay that information for the operator who sits right there. So again, that's nothing really that is so super cool to demonstrate. So we haven't got that in here. So that's more something that you want to actually experience putting some goggles on. But yeah, so that's obviously very important. And currently, the exciting bit of research is what is the right sort of modality? What is the right sort of immersion you want to give to people if they are actually operating this from long away? I saw somebody else also ask the question about what's the maximum distance you can teleoperate the robot. We've done the maximum for this sort of direct, actually, including haptic feedback teleoperation within the UK via a server in Ireland. So we've done that from Lincoln to Birmingham. We've done it from London to Lincoln. We've done it from just down the road, somebody's house, to the lab. That's all, feasible, possible. Indeed, latency becomes quite an interesting aspect of it. And there's interesting research questions still around this, how you facilitate this. So we've got a 5G test bed as well in Lincoln that we're actually starting to explore some of these opportunities that new communication infrastructure allows you to do, where you have actually low latency communication.
Yeah, I think that's worth noting that remotely operating that arm with haptic feedback, which means that you can feel some of what the arm is feeling, is a huge feat, and that's a huge achievement, because we've all had a video conversation with someone via Skype or Zoom or WhatsApp, and it starts to delay, or you start to get a roboty voice, and to actually be controlling a robot arm over distance using that same telecommunication network over 5G or 4G, that is a huge achievement. So.
And it's really tricky, I would say. Yeah. Also for the operators still. So there's an interesting aspect. So one of the side projects indeed is to investigate what sort of level of support, what level of autonomy of a robot grasping something you want to have when you are a novice who's doing it for the first time, grabbing this thing, and you may actually want much more support being guided, or when you move forward, when you've done this for 10 years as part of your job, the operators that actually do these sort of things right now, they need a very different type of support and autonomy of a robot than somebody who's doing it for the first time. Hey, Tom is back.
Okay. They're getting that is worth pointing out. Hi, Tom.
Hello. I've put the drone on a table behind me so you can see it rather than it hovering just over my head, making a really annoying noise where nobody can quite hear it. And also looking at the laptop screen, flying the drone behind me. That was a new one. I'm not going to do that again for this next session.
I'm sure that you had somebody with you to be your spotter.
I did. I had Suresh. He had the navigator's handset, and with the navigator handset, you can take over. So. Yeah,
so if anyone from the Civil Aviation Authority is watching, we were safe.
Yeah, exactly. And super safe now because it's powered down, just sitting on the desktop. So we did have it flying solidly for about 55 minutes, which is the sort of max capability for the drone. And of course, in 55 minutes, you can fly quite a long distance. I mean, this system itself at full speed, you can be traveling at, 60 mile an hour or more. So it's quite fast when you want it to be. And so you can go quite a long way.
Just a quick question, Tom. Somebody asked, what's the minimum size or intensity of radiation hotspots that the drone can identify? And I don't know how you answer that question because size and intensity, I don't know how they overlap.
Yeah, it would be intensity really that you're looking at. So we know with this system and in particular, which is using a cesium iodide detector, that we can spot sources which are something like 50% or maybe only 25% stronger than natural background. That's quite easy to distinguish. So for example, in the test that we've been showing on the video, that is literally 3 rocks about this size in a metal box, and those rocks are being collected from the Cornish Peninsula, if you like, and so they represent what we call norm sources, naturally occurring radioactive material. So they are extremely weak versus the kind of stuff you get on a nuclear site. And part of the reason that we test with these weak sources is because you actually need your system to be able to pick up very small anomalies, because you want to catch things early, really. Interestingly, though, when we did our NCNR work in Chernobyl, in the Chernobyl exclusion zone over the Red Forest, you could have flown this system at over 300 meters above the ground. In fact, I think it's 350 meters above the ground, and the detector would still be saturated. That's how radioactive it is there. Wow. So what we had to do in the field there, which is with a slightly different system because it wasn't with the DJI M300, we were using an M600, is we had to change sensors in the field to one which was much smaller so that we didn't saturate it. Because probably if you went to the wrong part of the Red Forest and decided to camp overnight, there's a chance you wouldn't be alive in the morning because of the radiation levels.
So that's not a nice place to be. Just another quick question from the comments. Mark, Tom said his drone will go about 60 miles an hour. It's just a question of how fast will your vehicle go? Can you keep up with him?
No, I don't want to keep up with him on the ground. With that, no. I mean, you know, as general, air traffic is faster than ground traffic. We could probably do 10, but I don't think we would.
As I say, slow and steady wins the race.
The point being, Pete, is I can cover a lot of ground quite quickly so that Mark doesn't have to. He knows exactly where he needs to go, and he goes route 1 straight to it.
Very true. So
but
indeed,
I can operate longer than he can.
Yeah.
He'll probably cover the same distance in total.
That's a very good point. That's a very good point. Tom can quickly survey the whole area, which allows Mark to go as the crow flies directly to that radiation source. Wonderful.
Probably not like the crow flies, because the ground unfortunately won't be necessarily even and all navigatable.
Right. Okay. So we're coming up to our last demo now. Believe it or not, we've done it 3 times already. So now we're going to go to our last one. Tom, I don't know if you can or want to put your drone in the air again, or whether it's actually reached its limit. And
I've got to keep it on the ground for a little while longer because it's been flying for about 55 minutes, which means it needs to physically cool down. So I got a partial warning on the system as I landed to say it's hot. I need to cool down for a bit, which is quite useful to have that capability. If we were flying it in it overheated, what it actually does is it just returns to its takeoff point and lands itself autonomously, which is quite helpful. But for this demo, Pete, I hope you don't mind. I'm not going to fly, but I've got the drone right next to me so you can see it, of course. And you'd be forgiven for thinking that I've got one of those Zoom backdrops, but no, this is real behind me.
It's a rather beautiful view.
It's nice. It's quite windy. This is the Fenswood Farm facility owned by the University of Bristol. It's 245 acres. And that allows us to take drones out either on their own or in swarms and to augment them with different sensors. So this drone that I've got next to me is DJI M300. It's their newest drone, and it's designed specifically for emergency response applications, which means it's pretty weatherproof, so you can fly in the rain. And it means also it can fly in quite high wind conditions, because you can't always guarantee that your nuclear disaster is going to happen on a nice day with blue skies like that we've got today, in fact. And so this system specifically that we've developed is essentially a microcontroller controlling a radiation detector, and that whole system is integrated with the drone platform. But we're using a Chromec detector. This is a D3S detector, which is actually 2 detectors in one. It's a cesium iodide, which is a type of salt crystal, which is a gamma spectrometer. So it measures X-rays and it measures their energies and it counts them. And then alongside that, inside this little unit, is also a neutron detector. So if you had a really bad nuclear disaster, you might detect neutrons. Most of the time, you'd expect never to detect neutrons. So if you do detect them, you're having a bad day at the office. So what we've done in this payload system behind me is we fully integrated a payload through the DJI Skyport, which is a port on the bottom that we can literally instantly connect and disconnect from, to sort of plug and play with this device. Now, this device on the bottom has a small HD camera, which looks straight down, and next to it, it has a ranging LiDAR, which is a point ranging LiDAR of 120 meters range. And that LiDAR tells us the height of the detector system above the ground. And we need that because we can combine that with the radiation data it's recording. And so from, say, 30 meters in the air, we can accurately calculate what the radiation at ground level is likely to be for human beings. And that helps emergency responders understand safe areas from not safe areas, if you like. So this system records at a 1 hertz rate all of that data. It takes the power from the drone, but it puts its telemetry through the drone's communication system alongside the rest of the drone's telemetry stream, and it comes straight to a pilot handset. And for this specific drone system, we actually have 2 handsets which are identical, one for the pilot, one for the navigator. And what we do is in the navigator's handset, we plug an iPad or an iPhone, and using an app we've developed, we can see the data in real time on a map. and that comes out as a snail trail. So I think Peter's going to show a video in a second of that snail trail. Now, for me as the pilot, I can fly the drone manually or I can fly it autonomously. And in my live heads-up display, I get the camera feed. So I don't see the radiation map. I get camera feed. But in an inset box, I get the counts per second for gamma, counts per second for neutron, and I get the height above ground data. And I can switch between cameras. So I can switch between a gimbal camera on the drone and the downwards facing camera on the payload so that I can see objects directly underneath the drone, if you like. So that's the handset capability. And you can see in the inset video, this is some data being recorded, and you can see that it's auto scaling as a heat map. And you can see a little red area there where we've got a small naturally occurring hotspot. These are rocks which are from Cornwall that have been hidden out in the field in a container. And if we fly over the area, forming like a grid pattern, and this is manual flying, but usually we do this autonomously, we can cover a grid square quite quickly. And so in a sort of morning of flying, you can cover a square kilometre with one of these drone systems over several flights. And once you've located a hotspot, you can then take the drone directly to where that hotspot is inferred, and you can then turn on your thermal camera, which is the system that is next to the payload. And the thermal camera, which is looking at heat, is able to show up any foreign objects or objects of interest which coincide with where the hotspot is located. And of course, what we can see here is we have an easily identifiable object which looks like a box, and indeed it is a metallic ammo box with 3 radioactive rocks inside. And so what we've managed to do is locate this object by its radiation. We've homed in on it by knowing its geolocation, and then we've, with the thermal camera, verified that it's an odd or foreign object. So we can do that with the thermal camera. We can also do it with the coincident HD camera. We can see there it's metallic, and that gives us a lot of information that we can then pass on to the ground team, which in this case is Mark. So we can pass on a location. We can pass on the type of radioactivity being given off by the object and how intense that radioactivity is, because that correlates to how dangerous it is. And we can also correlate an object, a specific object, which Mark with his ground team can then go and discover and hopefully take it away and make it safe. And that's the objective. So drones for surveying and ground robots for intervening, if you like. And so this is the system that we've got for you today. And hopefully you found that video very, very useful as part of our contribution. So Peter, back over to you, I guess, for any questions.
Wonderful, fantastic. Thank you, Tom. I was just fighting with my systems here. I've got 2 laptops and one of them's died, so I'm glad I've got 2. One of the questions would, where would these systems be deployed from? So where would you be deploying from? Would you deploy from the side of a road in a vehicle or an operations center? Where would you go from?
So when we've used these types of system in Chernobyl or in near Fukushima, for example, we typically take off from a safe area always, obviously, but that can be the side of a road, or because in exclusion zones, there's not really anything on the road, you can take off from on the road. And this particular system, you'd quite happily fly it out to about 7 kilometers range. You'd still get everything back in real time. But in the UK, of course, we can only fly within line of sight. So about 500 meters is as far as I would take it away. Already sort of routine flights in the UK. Of course, if there was a nuclear emergency, of course, with permissions, you'd fly well beyond line of sight in order to get really important situational data. So if it was a reactor that had gone wrong and there was a plume of radioactive material coming off it, that would be the kind of application where you definitely, as the operator, want to stay as far away as possible from it. And this drone gives us a very good capability because it can fly very fast, has a flight time of about 55 minutes, and it can fly in inclement weather as well. One of the things that we're working on at the minute via a PhD project linked to NCNR is the development of a system which can actually sample particulates which are in the air, so that you could, with a system like this, fly it into the radioactive plume and take a sample which you could then recover back to a government lab to understand what it's made of.
Wonderful. Thank you, Tom. Oops, sorry, I went through stereo on. Sorry about that. Okay, so now might be a good point to pass over to Mark, and we'll come back to questions at the end. Thank you again for that, Tom.
Thank you, Tom. thank you, Tom, for this good introduction, which is easy for me to pick up on, right? So we now have a map. We've grounded reconnaissance mission. We actually can get an overview of what the situation is like in a large environment. And Tom can provide us with an a priori map of the environment, which then is for us to start navigating in. So we may have actually some information already about which areas they are, and where indeed the particular objects are that we may be interested in. So then that's when a platform like, oh gosh, this is again me trying to point at equipment there, this sort of types of robots can come in useful. This is the Thorwald platform that we're using in a number of different applications. A lot of it is also being used in agriculture. So it's really a platform that's designed for the outdoors, can sustain the elements, similar to the drone that Thomas has just shown you. And we can take it out, and actually we've put a lot of effort into making this machine also move autonomously and be able to operate on its own, finding its way, avoiding obstacles, doing an analysis of the terrain to know which paths it can traverse, which one it can't, and so that we can not just remote control it, but actually trust this platform also to find its way in relatively unknown terrain. Peter, if you want to quickly show to the slides just for a quick run through, because also in response to the pandemic, one of the big challenges was we couldn't really go to as much in the lab and operate with one of our robots. So we've done a lot of work also in order to facilitate the ideas of digital twins. So here's one particular example where you can actually take a gazebo simulation and you link it to a real robot that is out there in the field, allows us to augment the scene with additional sensors and sensing things that isn't actually there in reality. Now that's super useful for the sort of setups that Thomas just described, right? He put a probe out there in the field. We can do the same. We don't even have to have a probe. We don't even have to have the sensor. We have an actual simulated radiation sensor that behaves very much like the real thing, and we can put in simulation probes somewhere dotted around and then explore our autonomous systems that can go about and do this sort of planning and autonomously move about a field and find these radiation sources. Gives you a similar result as we've seen from Tom, and indeed the sort of map that you get originally from Tom can then be augmented by actually feeding that as the a priori knowledge in there, and we can start refining that map by actually moving about in an environment, as you've just seen here. So this is just a meadow that we've got on our agricultural campus out there, and we've just put virtually some radioactive material in there that the robot can then find. Now, once we've actually found it, we can start trying to retrieve it. And there's different ways of how you can retrieve it. Of course, you can do work with autonomous grass planning, and you find an object and you try to actually move an arm there to retrieve it and pick it up. What we've been focused on in CERN, this is very much motivated by a lot of the requirements of the nuclear domain, is to have the human in the loop, to have a human operator in the loop, and rather than doing it completely autonomously, rather assist them in the job. What you see in the video here is actually one of our colleagues operating our robot that we've got in the lab, and operating that already from his own home. We've done the same sort of long distance teleoperation with haptic feedback so that people can actually feel what is happening on the other side. And we've done that also over long distances from London to Lincoln, from Birmingham to Lincoln, and vice versa. So in general, we can use this sort of setups quite neatly to offer this. And now we've put this very same setup onto the mobile robot. If you wanted to change over, I can probably give you a bit of a view of where we are. I'm going to use the microphone so I can move about. What we see here is the Thorwald platform, which we not only use, as I said, in NCNR. It's quite a sturdy one that can go outdoors. This one cannot really go outdoors because we've got a number of items, especially the robotic arm, that is not fully IP rated. So if you were to actually deploy such a system, you would swap this particular robotic arm out for one of the ones that we use outdoors. For instance, we use other arms outdoors to do things like strawberry picking. So this particular setup has also been just using, this is an actual strawberry bush that this particular platform was working on yesterday, slightly different manipulator, but then the same sort of mobile platform can go about and do other jobs. What we're going to do now is, following on from the story that Tom started early on, let's assume we have actually found the culprit. We've found an object that is in
in an environment, we've had this sort of mapping exercise, and we've got a good idea of where we need to go, then we can actually have an operator, like this gentleman over there, Soran, who will try to actually, through some teleoperation, then retrieve this object and manipulate it. So it's a mixed system, or we call it mobile manipulation. So we will first actually command it to steer towards the object, which we can do now, I believe. In general, this space is an omnidirectional robot, so in that sense, quite agile. It can also navigate quite complicated environment, turn its wheels, and can move also in quite tough, muddy, or whatever terrains. And then we're switching to a teleoperation mode, where Soran is using basically a twin of the same robot, and he can feel forces from this system, so he can feel whether he touches something, whether he lifts something up, and can operate this directly from, in general, long distances. You see, he's not quite far away right now, but we have also done a lot of work in augmented reality and virtual reality, so that we can provide him with an immersive experience, so that this sort of teleoperation can also be done over longer distances and at a safe distance, so he doesn't have to be there. It's strange, the other camera you get shows me from behind. I'm not quite confident with that. I'm going to move around. Right, so that's the sort of tidying up you want to do. General principles and general kind of fundamental research underpinning a lot of the work. While this looks simple, I'm actually providing the operator with the proper force feedback, and also using forces to convey additional information about the object position, for instance, can be super useful to support operators in this quite challenging task when they actually are not directly on site. Well, you know, with radioactive materials, you do not want to use your hands. And what is the standard state of the art very often these days is this sort of leader-follower systems, but often physical ones. So you basically just have very, very well-trained people that use a system on one side to operate something that is relatively nearby, but behind big slabs of lead glass that they may be able to look through. We're trying to support the operators much more through concepts of shared autonomy. So a lot of the grasping may actually happen completely autonomously, and then the operator can come in where specific dexterity is needed. Yeah, so that was our little demo. We have got to give you a quick round through the lab, because we do a lot of other bits of research. So there's an autonomous forklift truck. We're doing quite a bit of in logistics. You've seen the sort of areas of agriculture, where like strawberry picking is a big part of it. We've got these sort of teleoperation and in general manipulation setups within the National Centre for Nuclear Robotics. We work very closely also with our colleagues in Bristol to work on augmented reality and virtual reality to give operators like this gentleman a bit better immersive experience. And then, of course, for all these sort of supported or shared autonomy concepts, you really need also the ability to plan for manipulation autonomously, so that we can actually decide which configuration should the arm go into to pick this object, so that we can then support the operator to follow a trajectory that actually will be successful. I'm going to move you back to my other computer.
Yeah, wonderful. Thank you for that, Mark. Mark's just going to unmute himself on the other machine. I'm going to add Tom back in as well. There we go, Tom. Mark, you back on audio?
I'm back.
And then Ricardo, I don't know if you'd like to join.
Yep. Hi.
Hi, Ricardo.
Get the team in. Let's get Soran in as well.
Yeah. Bring him over.
And we've got Suresh as well. Suresh can come in.
Hi.
And
Okay,
in fact, we've got another drone up in the air at the moment. I don't know if you can just make it out. Over there.
Yeah.
Yeah. So we've got two M300s at the moment. One flying and then one directly behind me.
Is that one of yours or just somebody else who's randomly near you?
No, it's one of the team.
Yeah, wonderful.
Yeah. they'll fly it quite happily at height.
We're not going to have an air prox. Okay, wonderful. Thank you very much, everybody. We've only got 10 minutes left to this live stream, but I just really want to say thank you to everybody here, Suresh, Ricardo, and Professor Mark Hanheider and Professor Tom Scott. I think that you all put on a fantastic demonstration. It's extremely hard to get these systems to work in a lab.
Don't forget the expert operator, Soran.
And Soran, yes, Soran, because you've done a fantastic job at picking up that object, and you've obviously spent many hours learning.
He didn't drop it once the entire time.
No.
I mean,
so if there's a nuclear disaster, we want to send you guys.
You'd want Sarong and Suresh, because they're the guys who do all the heavy lifting on these types of projects. To some extent, us academics come in and communicate what we're doing and take all the glory, but actually all the credit is due to these guys, because it's, you know, weeks, days, months of hard work to get to the point where we can confidently demo systems indoors and outdoors. So it's a big thank you from the academics to their research team, I think I would say.
couldn't say it any better. Not going to repeat it. Yes.
Definitely. These guys spend, these men and women spend hours and hours and hours in the lab, usually throughout the nights and throughout the days. And especially when professors or people like me say, can you put this demo on? And then they have to work even more hours on top. So we are very appreciative to the time that you spent on that. I think everyone's done really well. As I say, it's difficult to get these systems working generally, let alone getting them to work in the middle of a field or on the spot 4 times for a live demo. So I think you guys have done absolutely fantastically. Just the questions in the chat, I think we've covered most of them. We spoke about the top speeds and the types of issues and different weathers and where you're going to operate from. Is there any other interesting points that you guys would like to point out before we finish, or any other information that you'd like to put out there to the wider community about your lab and where they can access more of your work?
Mark, do you want to go first?
I'll go first. I'm going to say a few things. So first of all, Lincoln Center for Autonomous Systems, we do a lot of different research in the area also of agriculture, as we mentioned, logistics. We are also having a CDT. So if there's any people out there that are considering doing a career in robotics in the wider sense, and in agriculture, and specifically, you want to look for the CDT Agri Forwards if you have about to come to an end with your other university studies and actually want to do a PhD. That's a great opportunity. I'm sure Tom will say something similar very soon. And we're also hosting, for those who are already a bit further in their academic career, we're also doing a conference called Towards Autonomous Robotic Systems, which is the TAROS conference, which will happen early September. And if anyone is in there from that sort of, general scientific community, we are currently planning to do it as a hybrid event, which means there will be a chance to actually physically come to Lincoln, which is a fantastic place to be, and actually means you can feel haptic feedback in robots, which I can't offer you right now. That's enough of my advertising.
Just to be sure, CDT is that Centre for Doctoral Training?
Oh, thank you. Yeah, this is us. Thank you. Yes, of course, that is the Centre for Doctoral Training. If anyone wants to do a PhD with us, or with Cambridge, or with East Anglia, because they are our partners in that particular CT, which is about agri-food robotics. That's said enough.
Thanks, Mark. Do you want me to follow that? So, yeah, I'm at Fenswood Farm, which is one of the nodes of the National Nuclear User Facility for Hot Robotics. It's also where we've got a new aerial robotics MSc starting in September, and I think it's still open for applications, although it's got a lot of people applying, in fact. But it's a great place to come and do and develop field robotic systems, mainly aerial stuff. So please do look that up. University of Bristol Robotics Lab, which we're part of. And it also has a CDT, which you all understand what that is now. I think, importantly, if you're interested in the kind of research that we do as part of our activity for NCNR, we will be travelling back out to the Chernobyl exclusion zone in September. We'll be doing some deployments of UAV systems, again, for a number of different interest areas that the authorities have highlighted for us to do surveys over. So please do pay attention to the NCNR website, and also to our sort of LinkedIn feeds as well, because there'll be videos that we put up throughout the trip, which is about 2 weeks, which will be videos of robot deployments in the exclusion zone, and in fact inside the new safe confinement, and inside unit number 4, which is the one which blew its top back in the day. And if you've seen the HBO miniseries, you'll have a good understanding that lots of robots were initially deployed and killed at Chernobyl in order to try and put out fires and scrape bits of nuclear fuel off the roof. So, you know, you get to see modern day robots deployed in a similar scenario. So please do pay attention to what we're doing in September.
Indeed. So as Tom says, we have our website, ncnr.org.uk, so please check that out. That will be updated soon with these videos and a number of other videos. I'd also just like to thank from my side, I've had a lot of technical support from Rui, who's behind me, behind the screen, who's helped me set up all these screens and streams and networks. So I'm very thankful to Rui for that. Okay, so there's a countdown going on of, I think, just 3 minutes left. I don't think there's any new questions, so I think we might just end there, unless you have anything else you'd like to add. No,
not much. We are looking forward to the last few months of NCNR, where we're going to bring these systems together and provide you with a kind of more complete solution.
Indeed. In September, we'll be doing some demos. So all of the systems developed through National Centre for Nuclear Robotics will be demonstrated in September, and we'll send out some information about that. So please look at our website towards September for an update on those systems. And again, thank you to everybody who's joined us today. Right then, so I'm gonna sign you all off. Bye-bye, Mark. Thank you very much.
Bye. Now Tom has shown it to me. I really want to go outside now. Tom has been out there for all the time. I shall enjoy that.
I think I'm ready for a cold beer. That's what I'm looking forward to.
You all deserve a cold drink. All right. Thank you, Mark. Bye-bye.
Thanks very much.
Thank you, Tom. Thank you for joining us. Thank you, Ricardo. Okay, thank you for everybody who's joined us here for the live stream. Very much appreciate your time, and I hope you've enjoyed seeing live robotics. It's not an easy thing to actually present live robotics. It's very, very difficult. Usually we do this at a live event somewhere around in London or somewhere else around the country. We can't do that this year, hence why UK-RAS have been wonderful at developing these live streams for us. So thank you to UK-RAS, and particularly to Claire Asher for actually bearing with us whilst we set up all of these demos. Thank you again. Take care. Enjoy the rest of your day, and bye-bye.